the east side party like we do.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
This problem is a typical example of conservation of angular momentum, or you might even think about it as a linear momentum being converted into angular momentum, if you will. So what we have here is that a door is at rest initially, seen from above here. And it's stuck at its center by a handful of sticky mud. So the pile of mud sticks in the middle of the door, and we would like to know what is the resulting angular speed of the door. So let's calculate the angular momentum of the piece of, or the pile of mud relative to the pivot point of the door. So it has, or in general case, it doesn't matter how far the mud is from the door when we consider this. So that's the position vector of the mud and the velocity vector. And so we consider it as a particle, so its angular momentum is r crossed by mv. And from here, we are only interested in the magnitude of the angular momentum here. So in that case, the cross product becomes m times rv times the sine of phi between those two vectors. So technically the sine phi of phi would be here, but let's say if this is 30 degrees, and that would be 150, the sine of that angle is same as sine of that angle. And what we are really after here is the r sine phi. So this perpendicular distance. That is also called the distance of closest approach, or the lever arm, if you will. And we know that that is just the half of the width of the door, so L2. Hence we get m times v times L2 for the angular momentum of the mud before it impacts the door. What about the angular velocity or angular momentum of the door? So in the overview video, I claimed that for object that is symmetric about the axis of rotation, the angular momentum is simply the moment of inertia multiplied by the angular velocity. But as we can see, this door is definitely not symmetric about the z-axis or the axis of rotation. So is this relationship true in that case? So let's think about this way. So here we have another axis of symmetry in the other direction. So, and let's have our origin here. This could be x-axis, for example. And now let's consider 2 points that are symmetric about this axis in the door. So like, for example, here, so x means that this point is, well, this is in fact the velocity vector of that point. So this means that it's going into the screen. And so the velocity vector is directed into the screen. So, and then we have the position vector here. Let's call this R2. And if you take the cross product of R2 and V2, you can use your right hand rule. So you point from the origin into this point, so diagonally down to the right, and you curl your fingers towards the velocity that is into the screen, and your thumb will end up pointing in this direction. So that's the angular momentum of that point of mass for that piece of the door. So let's call it, that's a bad subindex, let's call that R3. So that is L3. Same thing, the other point that is symmetrically across the x-axis So it has position vector R4, and its velocity is also into the screen. So point our fingers from the origin towards the X, curl our fingers into the screen because that's where the velocity is. Then we say our thumb points to the top left. So the angular momentum of that point in the door is in this direction. And now because of the symmetry, the magnitudes are, of course, the same, L3 and L4. They are going at the same velocity, and they're equally far from the pivot point or the origin. So as you can see, the L3 and L4 are off axis. So they're definitely not in the pointing in the direction as the same direction as the angular velocity vector, which is aligned with the rotation axis. But when we add those two together, L3 and L4, we see that their sum is indeed aligned with the angular velocity. We can repeat this procedure for any 2 points or pair of points across the symmetry axis, and their vector sum will also add up into a vector that is aligned with the angular velocity. So we can go ahead and use this relationship for the angular momentum. And note that we could have even have the door shaped like this, so the axis of rotation would be somewhere within the door, and in the same way the point here would cancel, or the vector sum of these 2 points, their angular momentum would add up into a purely vertical component. So we are saved by the symmetry. But for example, if we started chipping pieces away from this door, then this symmetry would break down and this relationship would not hold. But we are good to proceed back into this problem. So what do we need for L2? So we need the moment of inertia after the impact, and that's going to be the sum of the angle or moment of inertia of the door plus that of the mud. So like this. So if we add these two together, so from the door, for the door, we have from this table that is 1/3 of the total mass times a squared, where a is the width of the door, as we see from this figure. So for door 1/3 m, and the width of the door is L, so we have L squared plus that of the mud, that's mv. Oh, that's not the moment of inertia. It's of course a mass or particle mass, so its moment of inertia is m times the distance squared, like this. And then we get L squared as a common term, and we have m/3 plus the smaller mass divided by 4. So the width of the door is 1 meter squared. Door is 40 kg divided by 3, and the mud is ½ kilogram divided by 4. We get total 13.46 kg m squared. And we see that the contribution of the mud is pretty small because it's so light. So, and that was another question in this problem. So does the mud make a significant contribution to moment of inertia? No, it doesn't. But we have it there anyway. And now momentum is conserved, so L1, the magnitude of L1 is same as magnitude of L2, and we get mv L over 2 from here, and from here we get for L2, so I2 times omega 2. And we can solve for omega. Well, that is not a vector anymore. So omega after the impact, that's going to be mv L divided by 2 times I2. So the mass of the mud, that's 0.5 kg. Its velocity is 12 meters per second. And the length of or the width of the door was 1 meter divided by 2 times 13.46 kg m squared that we calculated. So the kgs cancel, the meters squared cancel, so we have units 1 over second that we expect because it's angular speed, and the magnitude is 0.22. So 0.22 radians per second is the angular velocity right after the impact.
Later, later.